sound will, I think. Now, can you see?
Yes, sir.
Okay. So, good morning. So, today we are going to discuss about incompressible flow through the pipes. So, mainly in all industrial flows, goes inside some closed channels, be it pipe, be it the duct. So, pipe is most commonly used actually. So, because it is easy to construct compared to the duct. So, references of book you already know actually Eunice Angels, MacDonald Fox, and Young actually, Macabre Smith, Ron Darby, and Neil D. Neighbor actually. So, what we have here, so first the liquid and gases. So, mainly either you heat for heating or cooling, that is one thing. Second thing also, even if you are not doing heating or cooling, you flow through in a closed channels because what the purpose is you want to drive them at a particular velocity or to give them some pressure. So for that your area should be confined, otherwise you cannot pressurize it. Second part, because without pressure the gravity is the only for driving force, just like open channel flows, river or dam or canal. You cannot do anything except you can provide a slope, and slope by means of the gravity force will give you the resultant velocity. So the nothing much is there in your hand. So to avoid that, and moreover in case of open channels, there are always a possibility impurities, you can have dust and so many other things. So therefore all drinking water supply which are being supplied in populated areas, it always goes in the closed channels, actually pipes. So that's one thing, just to avoid any type of you can say impurities actually from outside. So you need a pump actually in case of means driving the flow in a closed channel also. So in case of duct, you can also have without pump also, because you can have a gravity type of the slope, just like a distribution of water from an overhead tank. So all municipality waters or hostel supply, you fill up the water in the overhead tank once. After that, you just open the valve and you get the supply. Okay. So that's also possible. So in that case, you have only one time pumping cost, and throughout the day you are draining the water. But in that case, your pressure head or pressure is fixed. You cannot change it actually. So whatever is the height of that particular tank, that much is the pressure you can avail at the exit. Okay. Now, what will happen in case of pipes? You have so many connections. Pipe would be rough inside the from the inside. You might have seen that outside of the pipe, that the smooth surface most of the time polished in order to avoid the corrosion, rusting, and so many other parts. So you have polished surface from outside. If you see inside, all the time all pipes are rough, be it concrete pipe, be it metal pipe. Plastic pipe you will find smooth, actually just like a PVC pipe or let's say glass pipe. So glass pipe, no problem. Actually, this is the smooth from outside side also and inside also. But glass cannot sustain a very high pressure. You cannot put joints also frequently, and it cannot sustain very high impact also from outside, because once you will bury the pipelines, so anything can happen, something, some heavy load can pass. So metal pipes and concrete pipes are preferred. In case of water pipelines, in case of populated area or something, most of the time water pipeline is being preferred by concrete pipelines, because in that case you are maintaining the temperature inside the pipe in order to avoid excessive cooling or excessive heating. It will help in both the ways, and all the time all pipeline are being buried inside the ground actually, by a cover of, let's say, 2 to 3 feet. It has two purpose. One purpose is just to avoid excessive heating or cooling from outside environment. Sometimes you have some fire somewhere outside, so your pipes should not get heated unnecessarily. At the same time, in case of cold climate, you are not supposed to freeze the liquid flowing inside, because the water freezes at 0 degree actually. So in that case, once your water would be frozen and you are pumping from one of the end, so excessive pressure would be built up in the pipeline and it will burst actually. So to avoid those failures also, all the pipelines are being buried and are being provided sometime a cover actually, so that to avoid outside heating or cooling effect. Okay. So you need a pump. So you have to calculate how much is the pumping need depending on the pressure at the exit end, what pressure you want. Suppose you are providing a supply to a distillation column or a reactor where you have already some pressure inside. Just like inside your mouth, if you can close your mouth, you have some pressure inside your mouth. So nothing will go in until unless outside pressure is not more than that, right? So same thing in the case of pipeline. Pipeline, you will connect some reactors, some columns. So if pipeline pressure is low, so something would come out from column to the backside. So to avoid the backside thing, you should have something a pressure more than that. Just like in this particular pipe, let's say this is the inlet end and backside is the exit end. So if the exit end is pressure, let's say 100 bar, so this side pressure should be more than 100 bar otherwise the flow will not go from front to back side, because you should have more than that. So these are the things. So this is the actually the circular pipe first, and this is the rectangular duct actually. So this is also a closed channel comes in that category. So all your air cooled ducts and all this are being done by duct way. It is actually most of the time they have to provide frequent connections for that. So most of the time it is being preferred, but best one is the circular one to avoid the losses. Now, this part we already talked when we were solving the flow through the pipes by doing the momentum balance. So we have calculated their mass flow rate, average velocity also we have calculated that particular place. And this was the velocity profile inside the pipe actually. So this is actually a parabolic profile, right? This part we already did. Now, something we have talked about this thing, actually the laminar flow and turbulent flow in the introduction chapter actually. So how the laminar flows and turbulent flows. Why we are talking this? Because based on the type of flow, you will have some losses, the friction losses actually, and that need to be considered when you are designing the pipeline. So in this case, let's say this is the laminar flow. So you are injecting a dye. In your lab, you have a dye apparatus actually, Reynolds apparatus. There you might have seen the flow patterns of the dye. So you are injecting a dye with the help of, this is just some sort of a pitot tube type of thing. You are having a fine hole at the tip and you are injecting a dye. So dye is completely actually immiscible with the liquid flowing inside the pipeline, and uh, at the same time it should have a different color and with same density, so that it should not settle down actually. So these are the things, so that to make sure that wherever you will inject, it will remain at that place if your flow is laminar. So in this way, if you are injecting the dye here, so it is going just like a perfect straight line. So in practical, it doesn't come in that way. It slightly moves actually. So but it can be seen actually. Next is, let's say is flow is transient. You don't have the laminar flow, mean the streamline flow pattern is not there. So in this case, you will get this type of thing. So even if you say dye is moving, it's not getting dispersed completely inside the liquid. It's just following a zigzag path. So that comes in the category of transient flow. So this have also some losses. Now there one more extent, you just fill up a more and then this completely dye would be dispersed into the entire pipe, and that's called a limit of transient actually, the turbulent flow, sorry. So turbulent flow, as soon as the dye will come out, it will mix up in the entire pipe, and that's called turbulent actually. So Reynolds and how to means characterize whether we have the laminar flow or transient flow or turbulent flow. So this is being calculated based on the forces. What forces are we providing here? One, we are providing a force which will move it in this side. So let's say that is the inertial force. And then you have a viscous force. Viscous force is due to by fluids. So you are calculating the ratio of two. Once you are creating a disturbance inside anything, so that will try to rotate the fluid. So that comes the in the category of the inertia. Inertia is always try to rotate the things actually. Now, viscous force is the inherent property, or a viscosity is the inherent property of fluid or anything, be it if you want to means correlate by first law of the motion. If anything at rest, it want to be at rest, and anything in motion, it want to be motion. It doesn't want any change. So your fluid is also primarily at rest. So viscosity would counteract all the disturbance, whatever you are creating inside the fluid. So that is the viscous force. Inertial force you are providing from outside to create the disturbance inside the fluid. And the ratio of these two, inertial force upon viscous force, is treated as the Reynolds number, because this is in the name of the scientist Osborne the Reynolds actually. He has found this correlations actually first time. So Reynolds number is being calculated inertial force upon the viscous force. So finally for that the derivations comes out this dV rho upon mu. So you need to calculate all the time these factors, as I talked in case of flow meters also. So we say that you should have a Reynolds number greater than 10,000 to make it perfectly turbulent, so that you can get correct flow rate from orifice meter or venturi meter. So Reynolds number must be calculated all the time. Once it is calculated, then he gave some number. Based on that, if the number is less than 2100 in a straight tube, then flow would be laminar. And from 2100 to 2300, it is treated as transient, and 2300 onwards is treated as turbulent actually. Okay? Is that fine? Can you hear?
Yes,
Yes,
sir.
sir.
Okay. Oh. Now, this is what you have here. So it need a diameter, because you got the formula of the Reynolds number dV rho upon mu here. So you need density of the fluid, velocity of the flowing fluid, viscosity of the fluid, and diameter of the channel in which it is flowing. So in case of pipe, you already know the internal the diameter. What about this non-circular thing? Let's say a square duct. So in this case, the diameter is being calculated by actually the hydraulic mean diameter. So what are you calculating? That you are calculating area for flow. So let's say in this particular case, this is the square. So area for flow, if full duct is flowing, So area for flow is A square, right? Because complete area is A into A. So area for flow is A square. Now you have to divide by weighted perimeters, mean the perimeter weighted or in touch of the flowing fluid. So if you will say that if it is completely filled, so your fluid is touching this surface, this full surface, and this. So the complete perimeter being touched by this fluid is 4A. Okay. So your actually the hydraulic, the radius is called area upon weighted perimeter. So this is A square upon 4A, and hydraulic diameter is called 4 times of hydraulic radius. So you are multiplying here a factor of 4. Okay. So that way you will get here the area, means the diameter of this particular duct, which is equivalent to a pipe, is coming just A only. In case of pipe, it is coming D only, because the area of pipe is pi d square by 4. Weighted perimeter, because perimeter of a pipe or the circle is pi d only, so you have the denominator. So this area upon perimeter is called hydraulic radius. Multiply by 4 is being treated as the hydraulic diameter. Okay. So this is the way you will always calculate the diameter. By chance this pipe is half filled, what will you do in that particular case? Suppose this pipe is half filled, or let's say this duct is half filled. What would change in this particular formula? Can anyone suggest? Hello?
Area and parameter both will change in that
Yeah,
case.
both would change. In case of half, so the area would become a square by 2, I think, because it will become half
Yes, sir.
in that way. Now perimeter, because you have half of this, so a by 2. This is full a plus a by 2. So practically you have a by 2 plus a. So you will have 2a. So you will get 2a factor here, right? 4 will come here because 4 is just a hydraulic, the diameter 4 times of hydraulic, the radius only. So that way you have to calculate the hydraulic diameter. Fine. Same thing you can calculate for the rectangular duct also. So you have here the area in case of full capacity flow. So area is A into B. Perimeter of duct is 2A plus B. So that's what you have in the denominator. So AB upon 2A plus B is hydraulic radius. Multiply by 4, you are getting hydraulic diameter. Okay. So this must be used just to calculate the Reynolds number. Fine. Now,
Yes.
this part we already discussed actually, I am going to explain again. So once your flow is entering actually inside the pipe, so let's say you are somewhere far away. So you are flow from all confinement, there are no surfaces or nothing. So you will have a flat velocity profile, just like this. So this is just a outside of the pipe actually, you can say. Everywhere you have same velocity profile. The magnitude of velocity is same. As it will enter inside the pipe, it is feeling obstructions at the surfaces, and this velocity at the contact would become zero immediately actually. So you see the velocity here is zero. Uh, Velocity here is also zero. As you will move far away from the surface, you have some velocity, but it will take some time to get a stabilized velocity profile. So as you see here, you have full velocity throughout, then it is changed slightly. After that, it is further change, then again change, and after that, it got full parabola here. And if you will calculate velocity profile again here, you won't find any change. So this range from here, the fluid entered inside the pipe, and the length till it become fully developed means no change in velocity profile with respect to x further at a given position. I mean to say is that, so let's say you are calculating velocity at r equal to 0.2 here. And now you are calculating at this coordinate of x at r equal to zero point 0.2, your magnitude of this velocity should not change. So that's called a fully doubled velocity profile. Now this range from inlet till the point fluid reached the fully doubled velocity profile is treated as transient length, or that hydrodynamic entrance, the region of that. So in this particular range, no calculation is valid actually. Okay. So you should always avoid this length while doing the sizing of this, because this would give some error, because whatever correlations you are applying, those are not actually applicable for this range. So this range need to be calculated how much this part. Okay, in primary fluid mechanics, we just consider everything that okay, that in entire pipe the flow is fully developed actually. Fine. Okay, so this is called a boundary layer part, because you see in this particular part here the velocity is getting changed. In this part, this is the profile, then here and here. After that, there's no change. So this much thickness of the fluid, in this the velocity is getting affected by the surface, is being treated at the boundary layer. So we will talk boundary layer in the later on chapters, not here. Now we can calculate what should be this hydrodynamic entrance length, or some books say transient length actually. So there are the correlations as to the means there are the definitions here. So you have entry length here and hydrodynamic doubler flow, fully doubler flow here. So these are some the definitions which I have explained to you. Now this is okay. So this is what the shear stress would act. So shear stress would always act in the opposite directions of the flow, which because it will try to oppose the motion only, right? So this is the part we can calculate. This is being asked in most of the competitive exams. How much should be calculated? So there are the correlations for this actually. So this is the one for the laminar flow. So length of the pipe upon diameter is equal to 0.05 times of Re. So Re can be for the laminar flow can be highest value can be for the laminar flow with 2100 for the straight smooth tubes, and less than that it could be any value. It could be any value from 1 to 2100. So you should keep that value here. Based on that, you will calculate your length. For turbulent flow, this is being given by this. There are the several correlations for that actually. So one is this, that 1.359 Re to the power 1 by 4. Another one is this also, that L by D is the rough estimate. It is not being treated as a function of the Reynolds number. It is being treated, the flow is highly turbulent, so it is independent of that. So this is also 1 by L by D equal to 10. Some books you will find 50 also. So there are not very standard characterizations for turbulent flow here, but the laminar flow is fixed actually. L by D is to a 0.05 times Re only. This derivations of this, how to calculate this part, so we have solved these the momentum equations. In case of tubes, we have talked a long time back, but this is the another way just to do the force balance, and we ended up there this equation, right? The time we have solved the momentum equation in pipe. Do you remember this thing? We ended up with this equation. The time we have done the momentum balance in the pipe along the axis, याद है किसी को? Hello? Does anyone remember this one? No response from the entire class. Hello? Maybe you have some mic problems. You want to say something, but this is what we got actually. This is the another way just to do the force balance actually. So you have the shear forces. So in this side here, so you have here, this is the shear force component, this is the pressure. You are doing all balances here. Now body force is not acting in the direction of the flow because body force will act downwards and this flow is this side, so you don't have any component. So from this you are getting this the relation. So this is called cell momentum balance. So this part we already did. We integrated that and we got this average velocity and velocity profile in the pipes. So you already got this actually. So this is U max actually. U max is 2 times of average velocity which we have derived already. Okay. This expression also you already got here, that delta P uh, r square upon 4 mu L, 1 minus r square upon r square. That's what we have derived actually. Okay. Now, from here, if you will see here, you have a here term a delta P here. So this is practically is being treated as a pressure drop. So for that, the pressure drop, let's say you have two ends of the pipes, one is inlet, one is outlet. So you can put a pressure gauges at those particular points, and there you have actually pressure at point 1, pressure at point 2, and distance between 2 points. So practically you are calculating P2 minus P1 divided by the distance between the 2 points is L, and that's called actually your difference in pressure actually. So this actually, and then once you are calculating, so this is called del, invert of del. So if you want to get delta P, so you are calculating the reference from initial pressure minus last pressure actually. So this is upstream pressure, this is downstream pressure. So P1 minus P2 is being treated as the delta P, not del P. Del P is this actually P2 minus P1 by L. Okay. So this is being calculated here. So this is coming this 8 mu L B square R4. Do you know the from where this comes? This derivation is coming only from here, this particular part here. So here you have velocity, here you have this R square, this delta P by dx, and then you are converting this formula in terms of pressure drop only. Okay. So there we have wrote it in terms of Poiseuille equations, right? So this is what is being known. This is known as a Poiseuille equation also, Poiseuille equation, just to calculate pressure drop in uh, smooth pipes under laminar flow. So suppose, and this is the general correlations. Can anyone hear or not? Because I cannot get any the response from the class.
Yes, sir.
Yes, sir.
Okay. So now this thing actually you can rewrite it in this particular format. This is the general formula for any type of flow, be it laminar, be it turbulent, something. This is general correlation. A F, a friction factor, L upon D rho V square upon 2G. Okay. So this is the general formula of pressure drop given by actually Moody is actually. So Moody is the name of the scientist, and Moody or Darcy. So in that case, and this you have to equate with this one. Can you people equate this correlations of the pressure drop from here with this, and let's see what is coming here. Just equate this one with this. Can you tell what expression is coming? Anybody is doing?
Yes, sir.
Yes,
So
sir.
just equate this one and this complete thing and just bring this particular formulation in this particular formulate. Means for this you have to bring a term L by D. You have to bring a term rho b square upon 2, and rest of the things you keep it to one side, that will be treated as a f only. So so that you can compare this equation with this side completely.
So F is coming 64 by rho
This will
V.
come this much actually, 64 mu rho vd actually. So
Yes,
if you
sir.
will compare this properly, you will get. So from here you have just derived one thing. What should be the friction factor for laminar flow in the pipe? So this is 64 upon Re actually. So this dV rho upon mu is called Re, the Reynolds number. So this is how you will calculate friction factor in case of laminar flow in the pipe, 64 upon Re. Okay. So you have just derived this particular part. How has it come? Now this dynamic pressure is being calculated A tau upon rho b square, and the Darcy friction losses is being calculated in terms of meters. This is just in terms of meters actually. You have delta P, total head loss. So this is delta P is Newton per meter square. So that's called delta P. Now if you want to convert in terms of meter, you are the dividing by rho of flowing fluid and G. So this will be converted in terms of meter. So this is practically a head loss actually, okay, where F is Darcy friction factors. So in case of the laminar flow, it is given by this value 64 upon Re. Fine. So you know the friction factor by knowing the length of the pipe, diameter of the pipe, and velocity. You can calculate what should be the head losses only because of this flow actually, this velocity. You are not considering any the roughness here actually. This is just only because of smooth pipe. Okay. Let's say for turbulence. So practically, this is the, let's say you have the pipe, you have a length, you have a diameter, you have a velocity. You are supposed to calculate, let's say I am, means here I have fit a pump. I know the pump, how much power the pump is giving. So pump will have, let's say 1 horsepower, 2 horsepower, zero point 0.5 horsepower, or any capacity, whatever capacity of pump you have purchased. Every household have a pump. Yes or no? You have a pump there in a submersible pump also, right?
Yes, sir.
So that pump has some power. So power is being the mentioned zero point 0.5 kilowatt, 1 kilowatt, 2 kilowatt. It means that once you will give a electrical power to that, that is its power consumption. That much power it is being consumed. If it is ideally working, so that whatever power it is consuming, the total power need to be transferred to the fluid actually. Just like our body, if we are actually consuming, let's say 1000 calorie at a time, so it means we should work for 1000 calorie if it is an ideal system. But due to non-ideality, something goes waste, something goes waste energy and all this. So useful energy is slightly less whatever we supply. Okay, same thing happen for pump also. So whatever energy you are supplying by electrical means, first thing electrical energy is being converted into mechanical energy. So there is some conversion efficiency. So let's say most of the time that's convert to the 70%. Whatever we put this, so these days you have some the efficient pump, they convert up to 80%, not more than that actually. So 80% of total, let's say your capacity of pump is 1 kilowatt. So 80% is this. So zero point 0.8 kilowatt is being converted into mechanical energy. Now that mechanical energy is being transferred to the impeller of pump. Now that one, uh, some percentage of that would also be transferred to the fluid, not entire thing. The rest of the thing would be used just to rotate and all this. Entire thing cannot be used for pumping of the fluid. So it have the mechanical efficiency of the pump that would be near again to the 70%. Okay. So finally, that 70% of the electrical. So you have a power of pump is P. So power given to the fluid is P multiplied by electrical efficiency multiplied by mechanical efficiency. That would be the power delivered to the pump. Fine. Now you have provided a power and somehow you have developed a pressure at point 1 with the help of pump. Now you want to calculate what should be my pressure at this end, because I am connecting this to a some particular joint or a reactor where I have some pressure. So I need a pressure here at least slightly more than that. Otherwise it won't flow to the next reactor, because there you have a high pressure, this side a low pressure, so this fluid will not go in, or in that case the fluid from reactor would come back to the pipeline, which you don't want. Back mixing you are not interested. Okay, so you want to calculate what should be the losses in the pressure drop from point 1 to point 2. So we have just talked the pressure loss would be this F L upon D rho V square upon 2G. This is the general expression, be it laminar flow, be it turbulent flow, no matter what is that. Now you know the length of the pipe, you know the diameter, you know density, you know the velocity, at what velocity you are flowing it. So you can calculate this much is the head loss. Based on that, you can design, okay, what should be my capacity of the pump to get a desired pressure at point 2. Okay,
Okay, sir.
hello, right? So you are calculating what should be my head losses. Based on that, let's say this point pressure you want to fix up. This one P2 is fixed for you. So you can calculate P1 from here. You know the friction factor from the previous one, for the laminar flow. Turbulent flow, I will tell you the correlation just now. So you have the correlation to calculate this. So everything of this is known. P2 is known. So only unknown is P1. By using this equation, you can calculate P1. Once you know the P1, you can calculate power of the pump. So that much pump you need to buy from the market. Fine. So that's where you have to size your pump. Okay, what capacity of pump. ऐसा नहीं है कि आप मार्केट से कुछ भी पंप लाके आपने फिट कर दिया, it will work. It won't. Okay. So these are the things need to be taken care. Fine.
Fine, sir.
So this is the Poiseuille equation. So you should always actually the remember, and I asked this thing also in quiz also. So delta P is 128 q mu L upon pi d4. That is another format. Now these are the another correlations just to calculate that entrance length and exit length, because different books give this. So there are some variation for turbulent. So let's say, so for turbulent here, this is for pipe general correlation 0.06. We have 0.06 or 0.05, so not much change here. In entrance length, without any the Reynolds number for turbulent flow, 25 to 40 times of D. And you have to always consider the highest one, not the lowest one. Okay, so don't get confused with these things. So this is about we have already talked about. Now this velocity distributions, we already talked about this. This is velocity profile, shear stress also. Then volumetric flow rate we already calculated. This is your Poiseuille equation actually. We have already talked about this. This is velocity profile, and maximum velocity we did already. Actually, these are derivations. Now let's say energy. Actually, we are talking about energy on the flowing fluids. So what will happen that, so energy, a flowing fluid, what does it have? It will have a pressure energy, it will have a kinetic energy, and it will have a potential energy. We are not considering for time being any other form of the energy, means chemical energy and electrical energy and magnetic flux and all this. All sort of energy we are not considering. We are only considering these three form of the energy in case of our flowing fluids. So this here, from Bernoulli equation is the basis of that. to compensate non-ideality, we are just putting here a kinetic energy correction factor here and some losses. So generally, this is the ideal form actually, that P upon, you can put here rho g actually, P upon the rho g and B square upon 2g and z. This is the uh, energy in terms of what? Because here practically you will get mgh. So mg is weight of the flowing fluid. So mg has gone away from here. If you are writing in terms of z, so you are calculating energy of the flowing fluid per unit weight of the fluid. Okay, this is in terms of per unit mass. This is in terms of per unit mass, because mass has went away from here. If you will take out g from here also, it will become per unit weight. So these are the different the nomenclatures just to define your energy equations. So in case of ideal behavior, so if you are, this should be valid here in case of ideality. In case of non-ideality, you have to put a loss factor here also. Okay. Hello.
Yes.
How? So this is again the mechanical energy balance here in case of gasoline filling in a tank pipe. So this is another example here. Let's say you have filled a fluid in a tank, and here you want to take the outlet of that. So here fluid is at rest, no velocities or nothing. Pressure, gauge pressure is also zero because it is open to atmosphere. So nothing is here except your jet term. You are at a particular height, so it have some potential energy, that is your rho gh, okay, or mgh. Fine. Now what will happen at this particular point, the time the fluid will come out here, again it is going out to atmosphere, so you don't have a gauge pressure there. So you have your gauge pressure at that particular point is rho gh. But the time the fluid will leave from here, again your pressure would be equal to your atmosphere, right? So the whole thing here, the entire potential energy provided here is being converted into the kinetic energy. Okay. So your mgs term being balanced by your kinetic energy term. So you can calculate what should be the velocity coming out here. So that's what here, the maximum energy available to drive out the flow from here is mgh, because that is the component here. This much has bent down by this much height. That is the mgh, energy of the fluid. Same thing here also. Either you take the connection from here or here or here, the time you are having at the same datum level or a same horizontal plane, both will get same energy level, no matter whether you have connection from here or here. Getting the point? As far as your positions of the points where are the discharging the fluids are same, every point will get same energy, no matter whether you are making a hole here or somewhere from this bottom side. As far as these points are same, you will get same energy. So I hope we can end here. You might have the another class actually. Fine.
Yes, sir.
Anything you want to ask? So everything is fine so far.